And the turbulence is the only exception. It's a really lost, unsolved problem of classical physics. There is no statistical theory of turbulence. There is only Navier-Stokes equation. So we are late. Like a few centuries ago, statistical physics was born, and in principle, also statistical theory of turbulence could be born, but it wasn't.
Turbulence. It's one of the great unsolved problems in classical physics. But that might be about to change. In the following conversation, I speak with theoretical physicist Sasha Migdal, who recently came out of retirement with a groundbreaking new approach to turbulence. We discuss the powerful mathematical techniques Sasha is developing for describing fluids, and delve into his past life as a physicist in the Soviet Union, including his refusal to collaborate with the KGB and his eventual defection to the United States. This is the Escape Sapiens podcast. If you enjoy these conversations, the best way to support them is by subscribing. And now, here's Sasha Migdal. I hope you enjoy.
Escape Sapiens.
Today, what I want to talk about is turbulence. That's the ultimate goal. But before mathematics, before physics, I want to start with a few questions to find out more about you specifically. Right? So you were born just after the end of the Second World War in Moscow.
That's right. Meaning that I was conceived in anticipation of the victory in that war.
Is that what your parents actually told you? Is that true?
No, but it was obvious.
Well,
they married sometime before the end of the war, and I was born like 9 months later, whatever. So actually less than 9 months. It's an interesting story because I had some stress already in my mother's womb, and I was born at 8 months. But that made me that actually was started my improving my immunity by means of stresses.
But so was your father also a soldier then at all?
No,
because I know he was a physicist.
He was a physicist. He was involved in a nuclear project. He was one of those Kurchatov team who was involved in atomic project. Though he told Kurchatov that he would work on the bomb even only if there will be a gun to his temple, and so Kurchatov, okay, Arkady, he had a weakness towards my father. Okay, you'll do nuclear reactor.
So he worked not on the bomb, but just on peaceful uses of nuclear energy.
That's right, because he was pacifist all his life, and he was kind of very liberal in his views.
I see. But then, so for yourself, what was it like growing up in post-war Soviet Union, so in Moscow? And what was did you have a happy childhood?
Yes. Yes, I did. First of all, I was, born in the family which had interesting intellectual life, was pretty well, there was no hunger, and I lived in a separate apartment, which was a luxury. And my father took me with him to the skiing and later to the hiking in the mountains. So my father tried to inspire me to be physically fit and also intellectually fit, though he never had patience to teach me anything, but he kind of inspired me. He showed, my most important memory was when I was maybe 10 years old, when I was left with him, very rare thing. I was left with him alone in the dacha, and there was rain, drumming on a roof, and he was sitting at the table and working on his physics. And he just let me watch that. And periodically he exploded with laughter. It was happy laughter. And I said, what's happening? Oh, it's so funny. It works. It works. So he was a very emotional person. He told me that his normal state is either experiencing or expecting the wave of euphoria coming from his brain, I think. So he was very optimistic, and he enjoyed life, and that extended to all kinds of activities like hiking, like scuba diving. He was the first scuba diver in the Soviet Union. The the uh, this ID #1 because he founded the underwater. So he was a very popular person, and he also totally knew that and used that, and he was frankly a womanizer, like many other people in Soviet Union. So he was a home tyrant, and it was difficult to be his son. But then later I became his friend, and his friends were very lucky because he was a good friend. So when I stopped being his relative and became his friend, that's when our real friendship began, and that's what I remember now.
I see. And so he was the inspiration for you to go into physics then, or?
Not really. I had different inspirations. Until like 12, uh, I was thinking of being a poet and even wrote some poems. And I was, you know, I was, wunderkind is a bad word, but I was writing poetry when I was a little kid. And then about 12, I wrote a big poem uh, as a as a composition in school about Evgeny Onegin. It was written in the same, um, you know, style and same, poetry rhythm as Evgeny Onegin. So I had some gifts, but I buried them later. Actually, not completely buried because I still have my poetry on my website, but it's kind of mostly jokes. So I was inspired at an age about 12. And that happened when I wanted to be a poet, and I was writing poetry. And one day, I remember very well, my mother and father entered my bedroom. I usually slept late, uh, which was a very good habit. I didn't realize at that time. Anyway, they entered and said, Sasha, we thought and we discussed that we are not going to convince you to not to be a poet. It's a terrible profession in our country, and you are going to see a lot of unhappiness, but if that's what you want, so be it. And that kind of insulted me. Do they think I cannot be a physicist? So then out of, you know, out of childish rebellion, I protested to that, and then I got interested in physics and went to what's called Olympiad, and then eventually won some prizes, got acquainted with my uh, long longtime friend, Sasha Polikov. We both shared the prize at the Olympiad. And then, so that's how it started, out of protest to my parents, condescendence about be a poet if you want, but not a physicist.
It's funny because Polyakov himself is a fairly big name in physics, and throughout your career, you've sort of interacted with quite a few big names. And one thing I want to ask you about is you did your doctorate and you graduated at the Landau Institute. Right? And so for
Yes.
people who don't know, Landau is really one of these huge figures in physics. He's sort of like a Russian or Soviet Heisenberg or someone of this caliber, right? Very large guy. And you graduated, I think it was 1 year after he died or around this time. And so what I wanted to ask you is, what was the mood like at the Institute during that time?
It was a paradise. It was a paradise. I even wrote some memories called Lost Paradise. And that's about it. I mean, it was the best place I ever worked for, in spite of all the terrible things and the boredom and hypocrisy of Soviet Union. We were a little bubble of, you know, happy creative working. And the reason for that was our director, who was a genius of political intrigue. So he was married into the higher circle of Soviet bureaucracy because his wife was daughter of the famous revolutionary hero, and that, by the way, included his mother-in-law. He told me, Sasha, could you imagine she was running around the forest with this shashka, which means the sable, and her name was put horror into whites, and I am living with her for 40 years. So that's how it was. And he invented a scheme how to create the best place for theoretical physicists. It was after the death of Landau, sometime in 68. I joined Landau in 69, the year after, yes. So he said, he went to Politburo and said, look, these Western Jews are bitching us that we are persecuting Jews and that we are having anti-Semitism. The best way to counter this slander is to have a small place where Soviet Jews would happily work on important problems and will not be discriminated, and even sometimes allowed to go abroad. Of course, we will decide who goes and who stays home. But anyway, that would counter this lie about anti-Semitism. And it will cost you very little, because we are not going to even have a hidden military program. We'll just do a little theoretical physics, and that will cost you next to nothing. And they actually agreed to that. And that worked brilliantly, because indeed we were free. We were not really free, of course, but we even went abroad. He organized Soviet American symposia, so we became part of the world science. And indeed, there were mostly, well, not mostly, but just there were best talented people there. And that mostly were Jews. That's kind of the fact of life in Soviet Union, not just in Soviet Union. I don't have any preference. I'm not considering myself a Jew. I am a citizen of the world. But anyway, that was the fact. So there were some non-Jewish and people in Institute, and they had good biography, because he needed a party cell. So he was party member himself, and he invited few not talented people who were representing a cell of the Communist Party in the Institute. So it was a paradise, because we met each other. We did have no obligations like many other places. There was almost no bureaucracy. It was like a big family. And we talked to each other, we interacted, and you see this atmosphere, this environment, first of all, around us, there were talented people, famous apostles, followers of Landau, and we had no barriers between us. We talked and discussed physics and argued in front of those shabby blackboards with very bad chalk, which was, disintegrating in our hands. But it didn't matter. It didn't matter. So it was when most of the great things were done, like Higgs was done before, when Sasha and I were in the Institute, in the Moscow Physical Technical. But in Landau Institute, yes, we made some discoveries. At the same time, there were some big discoveries made in the United States and elsewhere. So it was a great time, and I was lucky to work with great people. Then in Princeton, I was also lucky to work with some great people. So I was lucky all my life.
Let me ask you about this, because I also have a doctorate in physics, and I'm working as a researcher in Regensburg at the moment in Germany. But let me just say that when I first found out about your work, I wasn't familiar with your earlier work. I first learned about you through your Turbulence work, and so when I looked through your Wikipedia page, I was shocked, right? Because here you're working in all different fields, matrix models, asymptotic freedom, QFT, all these different areas. And, I see that you're also connected. Your work that you did sort of later on was involved in a number of Nobel Prizes. So let me just ask you a little bit about some of your previous work. So you mentioned the Higgs, right? You submitted for publication with Polyakov in something like 1963, a paper about the Higgs mechanism. which is before Higgs, but your paper was rejected, right?
I cannot claim that it was before. It was because we don't have the manuscript. We know that it was submitted either in the the fall of 63 or in the winter of 64. He claimed that he made his discovery in summer of 64 and immediately submitted. It was published at the end of the 64. So look, I don't want to try to claim that we deserved Nobel Prize. If we didn't make it, it's a tough game. You have to be the first. We don't have the manuscript. That's it. But for myself, I'm quite proud, not that we made this discovery, but that we were defended it and didn't yield. We didn't even, like Galileo, we didn't even have to admit and then stomp the ground and say it still rotates. We just argued to the last moment, but nobody listened to us. All the Soviet school was laughing at us, saying that there is no such thing. Get out of here. Spontaneous symmetry breaking, ha, ha, ha. It was not a scientific argument. You see, it was so obvious that we were wrong that they didn't even discuss. And these were our teachers. These were great followers of Landau, Gribov, Oken, and they mocked us. They totally, not only they, so the paper was indeed rejected twice. It was first submitted in 63/64, don't know when exactly. I remember that in 63 we were finishing that work. That I remember vividly. But anyway, then it was, it takes, half a year to get it through Glavlit, which is censorship. Then it went to the journal. Then it was a Soviet journal, JTP. It was rejected by the referee on a totally wrong grounds. Then we modified it, resent it, and a year later it was again rejected. And the referee said something like, the authors will have to rewrite this paper, maybe complaining on the ignorance of the referee. Ha, ha, ha. And we did. And I know who that guy is now. He indeed was ignorant, like most of Gribov's students. Anyway, then he, after our second paper, there was a third one, which he finally grudgingly let be published, and it was published in 65.
So you mentioned that, so after that you were living in paradise as a researcher, discovering all different amazing things. But at some point, by the sound of things, things soured, right? So you defected from the Soviet Union to the United States. Can you explain what was it like working as a physicist towards the end of the Soviet Union, and what was it that eventually caused you to decide to leave?
Well, I can tell you one episode which was decisive. So first of all, I impolitely refused the offer from KGB to collaborate, and they felt offended and they closed all my foreign trips. That was one reason. Another reason was that the whole moral atmosphere in the Soviet Union was getting worse and worse. First of all, it was this hypocrisy, this lack of morals, literally lack of morals. I'm quite libertarian, but it was too much for me. And then there was some moment when I wanted to immigrate to Israel, which was, of course, impossible because I was non-physicist and they wouldn't let me. But anyway, at the moment I decided to do that, my father invited two of his former students, or I would say disciples, whatever, Gribov and Oken. He invited to his house and asked me to come with. And he said, let's openly discuss in front of the people who both respect, why are you thinking of leaving Soviet Union? And I said something which I didn't think about. It was just came out of my mouth. I said, because I'm not happy with the moral climate of my country. And that was, as I later understood, that was the main reason. I felt that I'm getting dirtier myself, though I did not do anything politically shameful, but I wasn't dissident either. My father wisely told me, Sasha, it's a profession. You cannot be both a physicist and dissident. Because first of all, you will reach nothing, and second of all, you will disqualify yourself, meaning that you will lose your qualification as a physicist. And when you eventually go to the West, they would not need you, because it's not a charity. It's a big world, and you get what you deserve, not what you deserved 10 years ago. So you will not get anything doing. You'll destroy your career. It was, of course, right. So I invented the way out of the box. I invented the way to get out without harming my relatives, without harming Landau Institute, and without losing my family. So I quit Landau Institute and went to the place which is called Space Research Institute, and that was ruled by the very interesting person. His name was Sagdeev. He was party member. He was a really talented physicist, and he was advisor of Gorbachev. He was high-flying person. He also, by the way, defected. Not defected. He married the granddaughter of Eisenhower, so that you know.
Wow. Okay.
So he moved to America like a year after me. So anyway, I deliberately devised the plan that if I go there, I will be able to go to America for a long time. And if you go for longer than half a year, then they let your wife visit you to clean up the place and scare away all the ladies. That's their idea. And then we'll somehow smuggle our daughter and our dog, which we did. It was a long scheme. It's described on my page. I don't want to go in details, but the thing is, I went there under pretext of making map of Phobos. Phobos is one of the satellites of Mars and the Soyuz station. So both Sagdeev and I knew that I can do it in 10 minutes through the internet. But he kind of supported my application to go for a year to make map of Phobos from the American data. It was time when it was possible. So I went there, and in the middle of that time, my wife visited me, and we arranged so that totally unbeknownst to KGB, our daughter went to the Komsomol theater to California. And so we went there. I visited the Stanford University at the time. So we went there, we appeared in the audience, and then we kidnapped our daughter from the stage of the theater. And then, which is something I'm really proud of, I went to the KGB guy who kind of missed the whole thing and said, look, you don't want complications? He said, no, I don't want them. Then why don't we pretend you approved it in a spirit of perestroika? That's an idea. Because it was too late. He couldn't do anything. Kidnapping back, it was impossible. It was filmed. It was, a public event. That was my plan. And then, indeed, they approved it, and I went to consulate, and in the consulate, in Soviet consulate, they told me in the beginning that, oh, you want to extend your stay with your family? We don't think it's really necessary. I said, you didn't get it. It's my family, and I think it's necessary. And you are my consulate. You're supposed to help me. Nobody said that to them before. It was still Soviet Union. Their official role was to help, like every consulate. But of course they didn't help. They just imposed the rules. And the rule was that you cannot stay longer than you were approved for. So, and then they changed. They became friendly, and they were cooperating. And at the same time, this KGB guy entered the room with the consul and me and said, no, we talked to Moscow, and Moscow approved it, which was a lie. That's how it went. It was 1988. It was about near the end of Soviet Union, and KGB was too busy plotting against Gorbachev and everything, so they let it go.
And I suppose after the fall of the Soviet Union, it was no longer a problem anyway, right?
Well, it was a problem because the people, you understand that what happened after the fall of the Soviet Union, it was two Godzillas fighting each other, KGB and party. So the KGB won, as you know. Party was defeated. KGB won. So the same people, just different words and different colors. They now pretend they go to the church, they denounce communism, but they're the same people. They are even more corrupt. They are stronger.
You mentioned that you refused to collaborate with the KGB. What does that mean? What does it mean for a physicist at the end of the Soviet Union to collaborate with the KGB?
It differs. So if you're a low-level person, they probably would want you to write reports about other people. But at my level, that time, which I was a doctor of sciences and quite well known, of course they didn't want me to do that. The purpose was twofold. Purpose number one was have my signature in some files so they have control over me because they would threaten to release it, and that would make me ashamed. That was one thing, blackmail. Another thing was that I have to probably introduce some first category KGB scientists to some other people. So I would say, tell my friends, famous physicists in America, let me introduce someone, this and this. So that kind of thing. So I would be useful idiot or whatever it's called. So I would not really do anything bad. And that is why many quite decent people agreed, because they understood that it's just a signature. They would do nothing. But if you do that, if you lose your moral virginity, then you are different. Then you don't feel, you see, in order to create, you have to feel right. You have to feel clean. And if you have unclean underwear, you cannot really do it. You see, it's very important to feel right and not sacrificing your soul, even if you don't believe in God.
I see. And you got out clean, essentially.
Yes, I tricked them. I didn't have to do any games with them to go abroad like other people did.
So I just want to ask one more thing before we talk about turbulence. So what I also find interesting is you came to America, you were able to get into very good institutions, but then you left. You went away and you started companies, you did algorithmic trading and all sorts of things. Why?
There were two reasons. Reason number one was that at that time I was developing my loop equation, and that was approach to turbulence and also gauge theories. And I got very little attention, and nobody basically understood my theories. It was just, I was popular because before that I did something which got a lot of attention, which is matrix models of gravity. But what happened is my colleagues were, you see, it was like flat Earth. It worked. You see, Kolmogorov theory worked for 80 years. At that time, it was maybe 50 years. So it worked.
Okay, so we'll get into what these different theories are in a second. Just
okay.
Preface.
Anyway, there was a theory which was not proven, but everybody believed in that by repetition. And my theory contradicted that. So that's why they didn't even want to listen. Besides, my theory was very, exotic. It was based on some concepts which were not yet even recognized by the contemporary mathematics. So I didn't finish my theory. It was just the equation, some symbolic solution. So even my friends and smart people shrugged it off. Well, what can you do with that? But then 25 years later, so I kind of left physics, not out of protest, but because I thought, well, if nobody understands me, it's either I am crazy or they are crazy. So it took me 30 years to understand that I am not crazy. Or even if I am, that's okay. So anyway, I left to do something which doesn't require approval of other people. If your laser scanning works, nobody cares what are your formulas. So, and besides, I was adventurer all my life. I went to Siberia. I was dating bad girls. I was doing all kinds of things outside of my implied rules. So I was living in this ivory tower of Soviet elite physicists. And it was boring. Real life, little dirty life was outside. And I was always curious about that. And the most exotic thing for a Soviet intellectual was business. So here was this explosion of internet business and something which I dreamed about. So for me, it was temptation which I couldn't resist. And so I made made some startup based on some discovery I made, which is kind of totally trivial from the physics or mathematics point of view, but nobody did it. So I had some success, and a year later, I sold my company to another company, and I didn't let my investor rob me like all investors rob all inventors. So I got away with 60% of the company, and I got some money which carried through all these years. So then I made another money and wasted it also. So money doesn't stick to me. But anyway, money was a pretext. What I really was interested in is intellectual adventure and seeing new world of internet and solving hard problems. So the next hard problem was already the stock market.
I see. But then you came back in, I think it was 2018, because you wanted to solve a problem with turbulence. So before
No, it's not because of that. It's because I learned about experimental verification of my prediction made in 1993. I made some prediction from the loop equation. I predicted the so-called area law that you have distribution of circulation, velocity circulation. Velocity circulation is a very well-known thing, but measuring its distribution is non-trivial. It was measured using numerical simulation of Navier Stokes equation, which I will talk about later. Anyway, it confirmed my area law. And for me, that was an epiphany. That was the trumpet. And I quit all my businesses. And I got the grant from Simon's Foundation and went working as a researcher in the New York University. And yes.
Can I ask you about that? Because I know that you worked in algorithmic trading. Did you know Jim Simons? Was there, because
he was a good friend of mine. Yes, of course.
Well, this is why I was interested in asking, because to come back to research after years of being out it's very rare. It's very rare. It's quite an achievement on its own. So I was wondering if it helped knowing Jim Simons and having your background in algorithmic trading.
By the way, I never worked for Jim Simons, and our kind of relationship were just those of friends. Because those people who worked for him didn't have a real friendship with him. He was a tough boss. And, you cannot really be a good friend of somebody who pays you big money. It doesn't work this way. But in my case, we both decided that I'm not going to work for him. And we stayed friends, and it only increased later. So I don't think he stretched his moral rules to give me this Simon's grant. I wrote an application, explained that it is my turbulence theory, which now is being confirmed experimentally. I want to develop it further. So he gave me, not he, it is his foundation, of course. So they gave me the grant for like 4 years or something like that for 4 years. So it's good money. And not the good money by the stock market standards. It's like order of magnitude less, but it was enough to survive. Anyway, I went to New York University, and then I wrote like dozens of papers developing further my turbulence theory, not yet solving it, just developing some asymptotic formulas for the distribution of circulation.
Okay, then let's jump into turbulence. So really, really, really basic question. Why should anyone care about turbulence? Like, what is interesting to the non-physicist, to the non-mathematician, to the non-engineer? Why should they care?
Well, it is, even without this new latest development, it was some enigma. It is, let me put it this way. In this 21st century, most of the basic theories, the physics theories, are there. We are actually reproaching physics that it is kind of coming to an end. And indeed, there were all these great theories. There were Newton mechanics, statistical mechanics. Statistical mechanics was basically some asymptotic solution of Newton equation, saying that there is a Gibbs distribution which every large system following Newton equations would eventually satisfy. And that's a very well-known fact. Then there is a quantum field theory, which means, okay, let's consider this or that classical theory. And then Feynman and Dirac invented famous concept that you have to sum over histories with exponential complex weight, and there is a interference of the histories and all these quantum effects, like, including spooky action of the distance, etc., etc. So that was done and accepted in the beginning and the middle of last century. So there were all these theories. So what physicists did for the last maybe 25, 30 years was just solving. And solving means you either make a little model of statistical field theory or quantum field theory, and then you compute some consequences, or you solve some limiting case. But it's not like you have already basic equations. You have definition of statistics. You have definition of quantum field theory. Like QCD was a great achievement, but it didn't invent the concept of quantum field theory. So the basic theories are there. And the turbulence is the only exception. It's a really last unsolved problem of classical physics. There is no statistical theory of turbulence. There is only Navier-Stokes equation. It's like having Newton equation, but not having Gibbs distribution. So it is like we are late. Like a few centuries ago, statistical physics was born, and in principle also statistical theory of turbulence could be born, but it wasn't. What we have instead is a pile of dirty empirical not even facts, assumptions, which are, the more we study them, the less and less they correspond to reality. In other words, we have really like flat earth theory, some phenomenological theories which are not justified microscopically, which seem to work, and then they don't really work. So we had some kind of stagnation. So it's a last unsolved problem. Feynman, famous scientist Feynman, wrote in his book that it is the last unsolved problem of classical physics, and it is very important for all other sciences. Now, why I think it is important? Because it's totally universal. There is turbulence even at the level of the universe. There is turbulence in every ocean. In a glass of water, if you shake your cup, you will have turbulence. If you do it like that, you have turbulence. And if you fly, yes, do it. You will see it will swirl, and that means it will create a little turbulence. So it's a universal phenomenon, and people thought it's boring phenomena. It's some trivial scaling laws which would never be theoretically justified. They could only be measured. So it was like green grapes of the mathematics. Mathematicians were dreaming about doing that, but then, like maybe 40 years ago, they said, okay, turbulence is too complex to study mathematically. Let's study a simpler problem. Let's study the problem. It's called millennium problem. It's not turbulence. It is proving that sometimes the fluid just flows without any, there is a smooth solution under certain conditions. Like if you take a jar of honey and pour it slowly into the cup, it will not explode in your face. Prove it and you get $1 million. That's what mathematicians did. You see, they lowered their bar so that it is in principle doable. They couldn't do it still. But the real problem of turbulence is just the opposite. Find what is the statistical distribution, because we know it is there. It is in front of our eyes. And it's universal phenomena. But what I found, which I will talk about later, is that not only it is universal phenomena, it is a quantum phenomenon. It turns out it's a macroscopic manifestation of quantum mechanics, which makes it totally amazing. It also involves some number theory problems, so it is worth spending 30 years solving.
So then, let me ask you, maybe to set the context for people. What are the Navier-Stokes equations, and what would it mean to have some sort of statistical underpinning? Would that be a description of individual particles inside the fluid, or what is the what is the picture
just
of the
statistical
other way side? Sorry.
Okay, what is Navier-Stokes equation? So there is 10 to the 28, whatever, large number of molecules of water moving around. Now, their collective description, if you just consider statistical distribution of them at rest, it is known to be Gibbs distribution. And it's nothing interesting except when you approach some critical points when there is a phase transition between liquid and gas, or if you have a superfluid, whatever. So there are mostly rather trivial short-term correlation, short distance correlations, and it's something like it really can be described like a media. And Navier-Stokes equations is some modification of original Euler equations. Euler equations is just the way to write Newton's equation for each molecule and the collective motion which describes those motion, saying that each element of vorticity is moved by the common flow. It's very simple equations. Now, what was great contribution of Navier and Stokes, that they found out the missing term in that equation, reflecting the friction. Because when the molecules move, they collide with each other and they lose some energy, so the flow is dissipating energy because of some internal mechanisms. However, if you consider smooth enough motions with wavelengths larger than molecular distance, which is a lot. I mean, most of the flow you could see, of course, have much larger scale. So this large scale, you could look at the most general term you could add to equation, which would be compatible with spatial symmetry and have as little number of derivatives as possible. Why? By purely dimensional counting. The higher derivatives you involve in the term, the smaller would be coefficient in front of that, because that coefficient would correspond to the molecular distance. So viscosity is rather small, but it's the leading term. So the term which Navier and Stokes added to the Euler equation is the most general spatially symmetric term, which is basically Laplacian of velocity times some coefficient, which is different for different fluids, and it is called viscosity. So basically, it is the Newton equation with friction translated into collective motion of the molecules.
And so what makes it particularly difficult to solve? Like, why is it so tricky?
You see, because there is no mathematical technology to solve nonlinear partial differential equation. So there is hierarchy of complex objects in mathematics. So it's like numbers, integer numbers, rational numbers, which are solution of the algebraic equation, etc., etc. I mean, irrational numbers. And then there is something which is solution of the one-dimensional differential equation, like some function of derivative and argument equals 0. So there is algorithm of solving one-dimensional equations, and you could solve them with all practical accuracy, and nothing exciting really happens with them, with small exceptions, but those exceptions can be analyzed analytically. Now, partial differential equations is something indeed at the next level of the hierarchy. They, especially when these equations are turbulent. Now, what is turbulence? Nobody, I think, maybe except me, knows what it is. But turbulence is a sudden spontaneous stochasticity. In other words, you have a flow initially, like a fast flow, which is predictable and smooth, but then suddenly it becomes chaotic, and there are more and more vortices, and the people were fascinating with that for centuries. So it is a mathematical, Everest, which was not climbed, and that is one of the attractions, like Fermat theorem. Who really cares about Fermat theorem? Just because it was not solved, and there was a dramatic story, but basically, not only that. Fermat theorem is related to other fields of, branches of mathematics, and so is turbulence. Mathematics just doesn't know that yet. Turbulence is related to quantum mechanics. It's related to loop space. It is related to number theory. It reveals totally unknown before, links between different branches of mathematics. And I hope that I will be able to convince mathematicians in that.
Okay, so then, what's your trick? So you have these equations that are very hard to solve, this setup that's very difficult to describe mathematically, but you've come in with some tricks, and what does that picture look like?
It's not a trick. I would rather say it's a, discovery may be too grandiose word, but it's some insight. I just found the way, if you compare the turbulence problem with this famous ice wall from the Game of Thrones, and there are people trying to climb it, and they're sliding back. And I'm yelling from the top, guys, there is a back door. Stop climbing. Get out of here. We're just halfway. So that's what happened. It's not the trick. It's the hidden back door, which was missed long ago. And the thing is that it's called duality. What is duality? Duality is the equivalence of two theories which have totally different variables. And they're equivalent only in statistical sense, but not approximately, exactly equivalent. And the first duality was not in the real physics. It was in rather mathematical abstract thing. It was equivalent to certain kind of conformal field theory, which is a field theory with conformal symmetry, which has something to do with our old work with Sasha Migdal. Anyway, so there is a conformal field theory, and suddenly turned out to be equivalent to quantum geometry in a different dimensional space. And that mathematical discovery made Juan Maldacena, a former student of in Princeton, quite famous, and it was indeed a very important phenomena, though it is not observed in nature. Because none of these two objects, conformal field theory and this ADS, CFT, gravity is observable, unlike turbulence. Now, so what happens is that the closer you are to the strong turbulence, meaning the faster your fluid moves and more vortices are there, the more chaotic it looks. It looks like a totally impossible problem. But we have done that before, because if you try to solve Newton equations for the fluid, you also have impossible number of equations, impossibly complex trajectories, if you try to follow that directly. However, if you find the probability distribution, so probability is a remarkable thing. The more complex is your phenomena, typically the easier it is to describe statistically if you sacrifice details which are not repeatable anyway. So the thing is that nobody managed to find that description, gives description of turbulence. People tried. There are many, many suitors of Lady Turbulence. But she kept her heart, I wouldn't say for me, but for future suitors. Anyway, the thing is that the problem really cannot be solved by direct approach. It can be only simulated. What people do is take large cube, like 24 cube lattice grid, and then they replace the Navier-Stokes equation by discrete finite difference equation on that grid, and then they use some supercomputers, a lot of supercomputer time, and then get some curves. Now, numerical data and numerical simulation data are as good as the theories you have to fit them. You cannot derive the theory from experimental data. You could have hypothesis assumption 1, theory assumption model 1 and model 2, and you can tell which one is more likely. That's all you can do, really. You cannot, because if you try to fit something more complex than simple power by a power law, you'll get something, but you'll get totally fake powers. When Einstein invented general relativity, before that, there were phenomenological theories of relativity. They say that, okay, the gravity load is not 1 over r in potential. It's 1 over r to the power close to 1, and here is the best fit power, which explains all the data. You see, it doesn't work this way. The truth is not to be compromised. And like Hilbert said, if you let me assume that 2 and 2 makes 5, I will prove that witches fly out of the chimney. You really cannot replace correct equation with something which is a model or looks the same or even is approximately the same, because that little difference could lead to a world of difference.
Could I ask, do you mind if I stop and go back just one step? Because there's something that I'd like to touch on, and you might have a nice answer to this. So you mentioned this ADS-CFT correspondence, these dualities, and I'm going to ask you in a second what the duality is that you're playing with. But just in general, the mantra is that quantum mechanics is really something special. You can't model a quantum mechanical system classically. That's the idea. But here you're saying that you have a duality. You can go back and forth from one side to the other. And on one side, you have a classical system. On the other side, you have a quantum system. Just conceptually, how is that possible? How can you model a quantum system through a duality with a classical system?
The correspondence is that you take the temperature of statistical physics and make it imaginary. You suddenly get the same thing as a amplitude of propagation of the quantum system. So in statistical physics, there is no interference. All the alternative histories, it's not histories, alternative states that is system enter with different real positive weights. But if you make analytic continuation, these weights become complex. Actually, they become phase factors because they become the exponential of imaginary I times action divided by whatever, doesn't matter, whatever, Planck's constant. So the thing is that there is mathematical correspondence between classical and quantum physics, and that is what led Hawking to his discovery. He reinterpreted this known Schwarzschild solution as a statistical system. So there is already known correspondence between classical and quantum worlds, and it is displaying itself in the black holes. However, what I found here in Turbulence is new kind of correspondence. So there are 2 ways to relate classical and quantum system. One way is to say that you take, like they did, partition function, statistical sum, or probability distribution, just forcibly, analytically continue temperature to imaginary value, and that will formally give you the quantum amplitude. What I found is there is a different way to find relation between classical and quantum physics. Take the probability distribution. In our case, it's a probability distribution of velocity circulation over a certain loop. So probability distribution is a very well-known thing, like Gaussian. It's not actually, it's very non-Gaussian. But anyway, take it and make a Fourier transformation. I hope people know what's Fourier transformation. You take the probability, multiplied by exponential of I times some factor omega or gamma times circulation, and integrate over all circulation. It's a Fourier transformation of probability. And I presume people know what is Fourier transformation.
Well, can I ask you, so is the picture, just so I understand, you have some volume which has some fluid inside of it, and you can break up that volume into loops, as in a loop in physical space.
No, you got it wrong. Thank you for asking.
Yeah.
No, I introduced what is called loop space. You take all possible loops in that volume, which is much more than breaking space into loops. These loops don't tile the space. I take the three-dimensional space, and I take arbitrary loop. But at the moment, I'm not varying the shape of that loop. Let's take a circle. Say, if you have a circular loop, you have probability distribution of velocity circulation around this circular loop. If you have a square loop, you have different circulation. In general, for arbitrary shape of the loop, you'll have different circulation, which will depend on the shape of the loop. But it also depends on the value of the circulation. So my old theory from the 90s said that if the loop is large, then this probability distribution have exponential tails, and it depends on the area inside the loop. The so-called plateau problem of minimal area solved film. So that is the statement. But what I'm now telling you is if you consider the Fourier transform, which is average over all turbulent configurations of turbulent fluid, of exponential of imaginary unit times some gamma times circulation divided by viscosity. That's the definition of this Fourier transform. So you take average of all possible velocity field configurations, in other words, average of turbulent flow or space, and you only fix the shape of the loop, of course, and the value of circulation. As a function of circulation, you integrate over all possible fluctuations, which means that you're in fact integrating over all values of circulation. So that's it called Fourier transformation. You take the function of one variable, integrate over this variable with the weight e to the I omega x, and that gives you Fourier transform.
But so can I stop you just so we don't lose anyone? So you have these equations, the Navier-Stokes equations. My apologies for jumping in. You have the Navier-Stokes equations, which are some equations in 3 dimensions for the flow of some fluid. So you're following the velocity or something at some point in the fluid. And what you're doing is you're breaking that space up into all possible loops within that space.
Not breaking that space. I'm introducing the space of all possible loops and see what can I derive for the probability in that space. It's enlarging. I'm going from 3-dimensional space to infinite dimensional space.
That's right. So because there are infinitely many loops within the volume, and then you're defining some new parameters on these loops, and then you have some that allows you to redescribe the original equations in some easier way of some new set of equations which are easier to solve, but there's infinitely many of them or something like this. Is this the picture?
Yes, and that's not the completely novel idea, because whatever nonlinear differential equations were ever solved, they were reduced to linear problem in higher dimensional space. Famous things invented by Lux and then studied by Russian scientists Shabat and Zakharov was also reduction of the certain nonlinear differential equation can be reduced by linear equation in higher dimensional space, not infinite but higher dimension. So that is a trick. I went further. I found infinite dimensional space, and linearity of my equation in that infinite dimensional space is the key to the solution.
Mm-hmm. So you transformed a very difficult nonlinear set of partial differential equations into linear, very simple not very simple, but simpler, easier to solve equations in infinite dimensions. And so can you say in a few words what the duality is then? Well,
that's what I was about to say.
Yeah.
Let me finish my statement. If you take Fourier transform of probability distribution of circulation, then that Fourier transform is a complex number because you have the complex factor. Now, I claim that that complex number is the wave function of certain quantum mechanical system in loop space. So there is a Schrödinger equation, which I exactly derive in loop space, which is equivalent to the Navier-Stokes equation in three-dimensional space. So the trick is that I take three-dimensional Navier-Stokes equation, and I find that this is a very special kind of equation. It's not every equation can be translated into a linear equation in loop space. So that is the hidden property, hidden key to that hidden door. There is something in Navier-Stokes equation which makes it possible to write it as a Schrödinger equation in loop space. And moreover, this Schrödinger equation, if you look at this quantum mechanical system in loop space, if you kind of imagine your loop like a limit of a polygon, each loop can be approximated by a polygon. So if in terms of that polygon, my equations are equations of quantum mechanics with coordinates being vertices of this polygon. So polygon is described by vertices in three-dimensional space, and I have, if there are n vertices, I have n-dimensional system which with n, 3n coordinates, with n vector coordinates. So the miracle is that basically this Hamiltonian doesn't depend on coordinates, only depends on what's called canonical momenta. Canonical momenta in quantum mechanics is derivatives with respect to coordinates. So if your Hamiltonian would not depend on momenta, that would be very trivial to solve. That would be basically classical equation. But it's also very easy to solve in the opposite case, when there is no dependence on the coordinate. Then the solution is what's called plane wave, exponential of IP times x. So that's a well-known thing. However, equation is linear, so every superposition of such solutions is also solution, which is not the case for Navier-Stokes, of course. So the trick is the following. You study this equation, take approximation by n polygon, but then you don't make any approximation. You derive that Schrödinger equation, and you observe that it is solvable Schrödinger equation. And that's something which mathematicians would kill me, because it's heresy. But that's true. They can check it. It's a solvable equation, and the solution is exponential of I times some effective momentum, which depends on which is different for every point. And then you get the system of equations for this momentum, the time dependence. You see, Navier-Stokes equation is about time dependence of the distribution. So that time dependence of distribution will be reproduced if this momenta, which I introduced, satisfies simple algebraic nonlinear equation. One first order, I mean, it's now a simple system of one-dimensional equations with only time involved.
So before we started speaking, you mentioned that this is some sort of a heresy, right? So your work is controversial, not in the sense that people can't go and check it, but that it really does run against several decades of previous work. So
yeah, it is mathematically correct but politically incorrect.
So for the non, can
I'm
you
just kidding. It's not politically, of course. It just contradicts the traditions.
Well, so can you for the non-mathematician and people who are not researchers, can you paint a picture of what these academic beefs look like?
Look, you're supposed to study your equation, which is a first order in time, and it's second order in coordinates, and it's nonlinear. And the kosher way of doing that is to study it as it is, either sort of numerically or trying to detect, find some theorems of existence or something. Forget solving it. It's not solvable. There is no theorem that it's not solvable, but actually maybe there is, because I'm not solving it. You see, what I did is the following totally, dirty trick. I said, look, every physical flow actually is not smooth because there are thermal fluctuations. Every physical flow is actually evolution of the probability distribution, because it is a very sharp probability distribution to begin with, because there are these thermal fluctuations in proportion to temperature, so there is very small actually discrepancy. There is sort of small noise in the initial velocity, but it is there. So what happens is this evolution of this probability distribution evolves with time. And what is turbulence? Turbulence is when it suddenly expands and approaches some universal distribution which is analog of Gibbs distribution and which is something I want to find and which I exactly found. So you cannot really start like this millennium problem, say, okay, start with smooth initial velocity and prove to me that there is a smooth solution or lack of that smooth solution. I said, no, sorry, I cannot say because it's physically impossible. There is no such thing as smooth velocity. I start with the small, tiny noise, and then I will either prove or disprove that it expands and makes spontaneous stochasticity. You cannot get spontaneous stochasticity if you don't allow infinitesimal noise in the beginning. So I generalized the Navier-Stokes, the Cauchy problem for Navier-Stokes, by allowing for noise. And actually, there was a great mathematician named Hopf who already tried that half century ago in the previous century. He did not derive loop equations. He wrote some very general equations which are impossible to solve. They are as complex as quantum field theory or even more complex. That's why people thought that turbulence is somewhere at the hierarchy of physical theories is somewhere above the critical phenomenon, these phase transitions, whatever, and maybe below quark confinement problem. But it's not a solvable in quadrature. So when I present solution in quadratures, they just close their eyes. I don't know. It's indecent to look at that.
Can you explain? So one aspect I don't fully understand, just conceptually, in what way is your solution statistical? So you're following some distribution. Can you sort of flesh out that picture a little bit?
Well, I introduced the quantity, which from the very beginning is complex, which is exponential of I times circulation divided by viscosity, and times some coefficient.
So, do you mind?
Yes.
Can I stop you just for a sec? So the circulation is some flow around a loop.
Well, there's a Stokes theorem which says a circulation of velocity around the loop, which is line integral of velocity times element of the dot element of the loop. That integral by Stokes theorem is equal to flux through the surface bounded by that loop. So what I'm measuring is actually flux, but it doesn't depend on the shape of the surface, so it's a property of the loop. So it's called circulation around the loop. It's something which Helmholtz studied. People studied that before. But Helmholtz, for example, found that in the Euler equation, if you let the loop move with the flow, then circulation is constant. I'm not letting the contour move with the flow. I'm making this contour a fixed thing in space. Then, of course, circulation evolves with time, even in the Euler equation. And with Navier-Stokes, it always depends on time.
So then, tell me what you can do. So what does this mean? I take it that you're able to match experiment better than what previous people were able to do. And so what does it mean?
Well, it means the following. It means that I'm deriving time dependence of this probability distribution. And that's a very general formula. It can be analytically computed for arbitrary shape of the loop, but from that, I can derive the consequences for something which is very well known, which is called second moment of velocity. So velocity at point R minus velocity at the origin or some other point, because the difference, only this difference between distances will enter. So they take square of that difference of velocities and measure it as a function of distance and time. It's a function of two variables. So I derive explicit formula for that difference, not numerical. I mean, it has to be done numerically because it's a quadrature. It's an integral over complex loop of some ratio of zeta functions, and it's called Mellin integral. And then the integrand also involves exponential of another integral over the loop involving some functional determinant. But these are just standard technical things in quantum field theory. It looks scary, but it's calculable. What I claim, I have solution in quadrature. And that means that I can compute it with arbitrary accuracy. I used Wolfram's Mathematica to compute these complex integrals. Complex integrals are calculable using some saddle point technique and also some numerical methods tied, fitted for that saddle point contour. So it's from the point of view of physicists, that's done. Once you reduce the solution to the quadratures, you are done. And I computed that, and I compared that with experiment, and my solution fits experiment within a couple of percent, and Kolmogorov contradicts experiment with 100%.
Which
it's
was
not
the
even
previous
close.
alternative.
Well, yeah, this problem of second moment was studied by numerous works, and they all contradict each other because they all try to they all try to fit their data for Kolmogorov theory. You see, Kolmogorov theory was such a dogma that they just threw away the part of the data which doesn't fit the Kolmogorov theory. It's like you have your favorite grandfather's clock on the wall, and you say, well, it's actually quite accurate between 5:30 and 5:32. It shows correct time. That's what they did. They introduced very narrow interval. Well, it was not narrow because they had large errors. So it's called inertial interval, and then say, okay, there is something beyond that which is not universal. It's called dissipation. We cannot describe it, but in inertial range, we describe Kolmogorov. Now, I managed to compute results of some numerical simulations with much smaller errors using some mathematical tricks. And in my curve, this, there is like, I don't know, my curve of this effective logarithmic derivative, which is effective index of that moment. The curve goes like couple of decades in scale. So it depends on distance divided by square root of time. So this variable, logarithm of that variable varies for a few units. Now, a very tiny piece of that curve intersects the Kolmogorov law. And the rest is far away.
But you match it the whole way.
Yeah. So it starts from 2. Kolmogorov law says it's 2/3. It starts from 2, then slowly goes, then at some point it crosses 2/3 and keeps going further. So at that moment they say, aha, you fit Kolmogorov law. But their joy exists only for 1 millimeter of my curve.
And this is not the only result that you're able to match, right? There's some other result.
Yes, the most kind of classical result is experiments done back in the 60s when people do what's called grid turbulence. That's something very easy to understand. That's something, by the way, mentioned by Feynman in his lectures. You take a very, preferably wide, large tube and make the fast flow, but you don't want it to be turbulent yet because you have smooth walls and it doesn't create vortices. But then at some point there's a grid, the lattice, the filter. It's like you're filtering your pool with a filter. You're pumping water, but it passes through the grid, which is filtering out dirt. So it not only filters out dirt, but also creates little vortices, because especially if you make those grid oscillate. So they provoke creation of vortices at the moment the water passes that filter, the grid. And then it propagates further. And from now on, it starts dissipation because it's turbulence and there is a constant dissipation of the energy. And eventually it becomes laminar. It doesn't really stop because you keep pumping it. So it's a stationary process. But every element of the water just flies further and dissipates energy until it becomes laminar and there is no more vorticity. Then dissipation stops, of course, because dissipation is related to vorticity. So these experiments were done in a large tube. Then, of course, it makes those turbulent flow in a smaller tube, and then they measure all the distribution of velocity in that. So very simple conceptual experiment done in '66. And they found out that energy decays is time to the minus 1.25. Actually, they found a little error in that index, 1.25, when they considered transverse component of velocity, transverse to the flow. In the longitudinal, there was slightly different exponent between 1.24 and 1.27. So because they are supposed to be the same, I would say that if you average, you will get 1.25. Now, Kolmogorov theory never explained that. They tried themselves to stretch their data to fit Kolmogorov theory, and they claim something which is totally irrelevant. I don't look at their claims, I look at their data. So the data clearly says 1.25. And Kolmogorov theory, together with some other dirty phenomenological assumptions about correlations, produce 1.2. So if you really are willing to pray to Kolmogorov theory, say, well, it's close enough, and the rest is maybe errors. But they present their errors. The errors are in the third digit, not in the second. So they say it's 1.255 or 1.251, but it's not 1.22. So my theory says it's exactly 5/4. It's exact number.
But so the takeaway message is that in some turbulent flow, there'll be dissipation of energy according to some exponent or something like this, and you hit it exactly, more or less.
Yes, yes. Actually, I have correction also. I say that it's only one, it's the leading decay index. I have found the whole spectrum of decay indices. My kind of new contribution say it's not a single decay index. There is non-trivial transcendental formula, which if you translate that into series of decaying terms, they have infinite spectrum of decaying indices. And some of these indices are even complex, which means oscillations. And these complex indices are related to Riemann zeta function. So I have an analytic solution, and I could study asymptotic of that analytic solution at large time, and there will be correction to that 5/4. So there will be some higher decay index. I don't remember what was that. It is like 7/5 or something. Anyway, so there is another one, or maybe 11. I have it in my paper. So there is a correction. And indeed, they don't have exactly 5/4. There is some curvature in the beginning. So if those experimentalists or new experimentalists would ever give me their data, I would compare them with my theory, and I will check whether my correction also is correct. There is a recent experiment made this year, another experiment in water tank. This time, they didn't have this grid. They had some magnetic stirrers. So there was a big tank, and they stirred the water, and then at some moment they stopped stirring and dropped those stirrers on the bottom, and then it decayed from that moment. So they created turbulence and then let it decay. So my theory also applies to that. Now again, they tried to stretch their data to fit Kolmogorov law, but being honest in their heart, they published as an inlet in their picture, they published the data, what they called for large tank. Large tank is actually what I'm studying. Mm-hmm. It's infinitely large. I don't want to study the boundary effect of the fine tank. So for the large tank, their own curve has a slope 1.25. They actually claim that. They didn't say 1.255, they just said 1.25. But they also have correction, so I wrote them a letter, which they're supposed to present the results of their data. That's why they have such a, I know, because in my paper, I pledged that I will give data at request. So I wrote to them asking to give explaining that I have a theory, asking them to give me raw data so I compare with my theory. I didn't get any response. And there are similar things happening. Basically, whenever I talk about my paper, people are stunned. They say it's crazy, don't have any objections. And I have a hard problem getting numerical experimentalists or experimentalists to confirm my theory. It's not like they have a contradiction. No, there's only one person, my good dear friend Srini, Kitapale Srinivasan, who is actually performing that large experiment to compare my theory. He already presented me with a smaller scale experiment, which I present in my paper, which fits theory perfectly, but I want a larger Reynolds number, meaning faster fluid, and a larger lattice, which means more precise calculation, and then I will hopefully get better fit of my data. So preliminary results of his new work fit my data also, fit my theory also.
So one aspect of this, though, that you mentioned and I've seen in your other talks, is that you say that there's no blow up of solutions, so no explosion. What does that?
Thank you for reminding me that.
What does that mean?
That means that I can. So my solution for this effective momentum decays with time as 1 over square root of time plus some constant. And if constant is positive, it just decays, and in the end, it goes to 0. It's 1 over square root of t. That's the turbulence, decaying turbulence I found. Now, in principle, my equations also have solutions which could have a blow up. We'll have 1 over square root of some constant, t critical minus t. So there, in principle, is such a solution. You could go, substitute in the equation, it will pass through equation, but then there is coefficient in front of this 1 over square root, which depends on the curve, and the position of the curve. So you write algebraic, you get algebraic equation for that coefficient, and I can prove that this equation has no solutions. So I can prove that within my theory, there is no explosive solution. So if some mathematicians would prove that my theory in the limit of vanishing noise is equivalent to the standard theory, that person will get a Millennium Prize, and he will pat me on the shoulder for providing him inspiration.
And hopefully you will share a little bit in it. But
it doesn't matter. Look, I will be so happy if my theory will be proven right. I mean, you see, there is something in discovery which is incomparable with anything else. So I never was hunting prizes, as you can see from my CV, because if you don't hunt prizes, you don't get them.
So if you could explain again, just so I understand correctly, the duality that you have set up. So on the one hand, you have incompressible fluid, some incompressible fluid, which the dynamics of which are described by the Navier Stokes equations. And then that space has infinitely many loops within it, the volume of the fluid, and you are looking at circulation around these loops, and you can define some new parameterization, which allows you to rewrite the equations, the one very difficult equation, as sort of infinitely many very simple linear equations.
Not very linear, but not very simple yet. But it becomes simple. The linear equation, which is equivalent to the Schrödinger equation in space of all possible loops, which is a complex object because space is infinite dimensional, but it can be solved in terms of function of one variable, which is this effective momentum as a function of the angle around the loop. So, and moreover, time dependence of that momentum can also be solved exactly, unlike Navier Stokes, where you cannot do it. You cannot separate time and coordinates. So this is that I go to infinite dimensional space, and then I parachute down in one-dimensional space. So in order to get around that ice wall, I kind of fly around on a dragon. I first go to infinite dimensional space, then I find out the way to lead it to one-dimensional space, because the loop this momentum loop is a function of one-dimensional object angle on the loop.
Mm-hmm.
So that's exact transformation. So what is very difficult to digest for mathematicians is that something which they revered and studied for centuries is solvable.
Mm-hmm. And so can I ask, so on the one hand, you have a very classical system, just Navier-Stokes. And then on the other side of the duality, you have essentially the Schrödinger equation. Does the Schrödinger equation necessarily have to describe a quantum system, or can it just be describing a classical system which has the dynamics of the...
If there is exact mathematical correspondence, there should be also physical consequences. And I can tell what are these physical consequences. I have exponential of imaginary I times circulation divided by viscosity. And I sum over all solutions of my equation. And I can describe all these solutions parametrically. I know it is called Euler ensemble. I have found it, or a string theory. So if you have sum of exponentials, complex exponentials, you have these famous interference effect, unlike statistical mechanics. So I claim that if you study the right thing, which is Fourier transformation of probability distribution, then it is quantum mechanical object. The duality is not that the same thing, not that probability, original probability has complex things. No, probability is not the square of absolute value of psi function. Probability is the Fourier transform of psi function. So it is different correspondence, but phenomena are real. When there will be better experiments, and maybe there are already experiments, you will see these quantum oscillations. I predict quantum oscillations in the second moment of velocity. So there are observable macroscopic quantum effects in decaying turbulence. That's what I claim.
So then I have to ask you, so I want to move towards the end of the conversation, and I want to ask you a sort of a big question, which is, Navier-Stokes is nonlinear, but so is Einstein's equations, right? And so people have been trying to quantize gravity for a long time now. And so the big question I have is, can you take your framework, can you take your I'll say tricks, and apply them to creating a quantum gravity? Or can you, is there some gold there?
Yes, that is my dream. I haven't succeeded at. I actually mentioned that possibility back in the 60s. I wrote a report which called Stochastic Quantizations of Stochastic Quantization, where I said, well, it could be that, our gravity is some nonlinear equation in higher dimensions, and then some internal degrees of freedom became noisy, and you'll get spontaneous stochastization, and you'll get effectively quantum mechanics without actually introducing anything probabilistic. You just have the stochastic nonlinear differential equation, which becomes stochastic spontaneously. Now today, I still don't have explicit solution or any even draft. But what I can tell you is the following: the Einstein equation belongs to the category of equations like Navier-Stokes, which have the hidden geometric meaning. And these equations can be described in terms of loop space. And that approach to the gravity is known. I'm not talking about using loop space as basic variables. What I'm trying to say, if you consider the, trace of the operator of the parallel transform around the loop, that operator, that trace can be, there is a loop equation, which was written by my former student McCain long ago. And others wrote that. So you could write loop equations for Einstein. Now, usually it is not very interesting because gravity is weak. However, gravity says there is a naked singularity, and nobody resolved that yet. And one of the reasons why people go to string theory is that they don't want singularity. Now, in my case, in Navier-Stokes, there is also naive predictions of this finite time blow up. Similar thing, nonlinear differential equation, time derivative equals some higher power of variable, and if you can balance the terms, you'll find some power like singularity. And Einstein equation is no exception. There is a naked singularity if you naively take them. But what I'm saying is that in Navier-Stokes, at least, there is spontaneous stochasticity. You actually start with infinitesimal noise, and then it gets amplified. Instead of having naked singularity in Navier-Stokes, you have this decaying turbulence. So my dream is maybe indeed, in case of Einstein equation, there is also spontaneous quantization. Maybe there is also some spontaneous emergence of the quantum mechanics from relativity. Maybe you don't need to quantize gravity. Maybe you are, knocking the wrong door. Maybe it is naturally, spontaneously quantized. I don't have any proof. It's quite irresponsible for me to claim that. So I don't claim that. I'm just saying that now that I know there exists, there is no singularity, no blow up in Navier-Stokes, but instead there is stochastic spontaneous stochastization. Maybe similar phenomena takes place in gravity. And once I have a luxury of spending the whole year in the Institute for Advanced Study, I will definitely discuss it with great gurus of string theory and gravity which are present there.
It's interesting because you said at the very beginning that there is one classical phenomena that we don't yet have a statistical description of, which is turbulence. And so in some sense, if we're trying to quantize gravity without having this one block, it's like fighting with your arm tied behind your back, right? Because you're missing this one conceptual piece of the puzzle, potentially.
Maybe gravity don't need to be quantized because it's very difficult to quantize gravity. Whenever you try to quantize gravity, you're having mathematical problems. But if you have classical theory from the very beginning and it naturally produces quantum noise, it will be very interesting.
Can I ask just quickly for people who, well, actually, I would like to know the answer as well. The loops in your theory, is there any relation to the loops in loop quantum gravity?
No. Loop approach to gauge theory was developed in 88, 89 by McCann and myself. Loop gravity was developed about in the next decade. It was following these things. So there were Ashtekar variables. So there were already some dynamical variables. So loop gravity was inspired, but it didn't follow our work. It was independent development in a sense that they took what we consider loop, Wilson loop, as a basic variable, which we don't do. Well, we actually do that, but not for fixed place on the loop. We do it in the whole loop space, so it is uses some mathematical. So loop gravity uses some mathematical tools, but it developed totally different technology, trying to build the consistent gravity theory by quantizing this object. It's not what we did. It's not what I did in Turbulence, but chronologically, our work on loop equations and gauge theory and my review of that work in early 80s was before loop gravity.
So, to wrap up, do you have any advice for young? I mean, you left, you said, jobs which were extraordinarily lucrative to play, let's say, or to follow what you found interesting. And you've had a fairly colorful life, leaving the Soviet Union to get through to the United States. Do you have any prescription for people as a way of enjoying their lives and having impact and feeling good about their lives, when they're looking back on the past?
Well, I can tell one advice, which, not advice, but summary of the life of my father. It's not quite the same as my life, but still. I wrote to one of his old friends, which was in kind of quarrel, but then we made peace after that. But at the moment, I was kind of unhappy with him for something. So I wrote him, if the example of my father's life teaches us something, it is that not the power and wealth, but the love and beauty is what makes a person happy. And I still stand behind that because I had some, not large, but some share of wealth in this life. I wasted it all, not all, but most of it. But what I got from beauty and love and other real values is incomparable. I can compare the joy of discovery with joy of selling your company for several $1 million, and that is incomparable. So if you are capable of discovery, not everybody is capable. There are tests you have to put yourself. First of all, you see, making discovery is like make record deep diving. You have to be able to hold your breath for a long time and believe that you could make it up out to the surface. And then you have to go deep into your thoughts, and you have to follow the consequences of logic and not being afraid, because most of people don't even dive. They're just swimming on the surface, and they are having what's called lookup table in their brain. Here's a question, lookup table, answer, like ChatGPT. So logically thinking yourself is something you have to train yourself from the very beginning. It's like deep diving. And you have to be able to do that. You could test whether you do it, where you could logically think against prejudice of the environment, whether it's electing a president or finding a sweetheart or finding your profession. You have to really understand what you love, and then you could dive deep. And then you should not be afraid of your consequence of your logical sequence. Another advice I could tell is the following: that I'm proudly ignorant. I don't know much. I understand a lot of things, which means the following. In my brain, like in the brain of every good scientist I know, there is some, not bookshelf, but like three-dimensional, grid where with cells where you put data, and that data is a fact. So here comes new fact. You look up at your shells and find if it's already there. If it's there, you don't even put it. But if there are similar facts, you try to generalize your cell to accommodate that new fact, and then you slightly enlarge your cell. You don't really need that new fact. The main thing is those cells, those framework, those bigger concepts in your brain. That's what you have to remember. And if there is a new fact which doesn't fit any cell, then you have to seriously analyze it, you criticize it, then you maybe, find a new cell and put it in a new cell. But you have to be reluctant to remember things. You don't have to, and you should be able to forget things. But what you should remember is this general philosophical framework, how to understand things. So you have to train yourself to do that. It's as I said to my students, it's thinking is hard, but suffering purifies. After which they went to the dean and complained of child abuse.
Well, Sasha, it's been an absolute pleasure. Thanks for coming on the podcast.
Thank you. You had a very good question, and that's very important. It was a really inspiring conversation. Thank you.